And we're going to talk today about metadynamics and the way that metadynamics operates. And we're going to see how long I can keep this pretense that I'm max up. So, metadynamics. Let's start off. So this is the PLUMED workshop. We all know about PLUMED now. It's a plugin. It plugs into all these MD codes. It's written by Gareth Trebello, Carlo Cabelloni, Giovanni Bussi, and me, Max Bonomi. It does various enhanced sampling methods, free energy methods, and analysis of MD data. And it sort of came out of the metadynamics community, which is the method that we're going to talk about today. So we've talked about this business of the timescale problem before, of that we have in molecular dynamics and Monte Carlo, that we have this problem of these rare events that we can't sample in short MD simulations. And the reason that we have these rare events, there are two reasons. One of that there are high barriers and activated events, and the other issue is that there is slow diffusion. So all of these methods, the methods that Giovanni talked about last week, the method of umbrella sampling, and the method that we're going to talk about today, metadynamics, are there to resolve this timescale problem. And now I really need to take this off because it's crushing my head. So let's talk about what metadynamics does. At the heart of all these methods, and Giovanni talked about this last week, is a process of dimensionality reduction. So we have our atoms and our positions of all these atoms. This is these R's in these formulas here. And we calculate a small number of collective variables, the S's here. And generally we have one or two of these that describe important transitions that the system undergoes, the key sort of thermodynamic information we want to extract. And this is going to give us a coarse-grained representation of what happens in reality. So what we're going to do is we're going to try and construct the average energy as a function of these collective coordinates. That's going to be of our coarse-grained representation. And the way that we're going to do that is we're going to average over all the other degrees of freedom in phase space. And this introduces us naturally to this idea of the free energy, F of S, which is given by this formula minus 1 over beta, the logarithm of the probability, and the probability we construct by building a histogram. And we can calculate that probability just by doing the normal business of, the bread and butter of statistical mechanics, taking an ensemble average, which is what's going on in that formula at the bottom. Okay, so some examples of these collective variables that we might use. So if we're looking at, say, this reaction, we might have this dihedral angle here, which tells us whether or not we're in trans-azobenzene or cis-azobenzene. We can use, let's suppose we're looking at protein folding, we can use something like the gyration radius or the number of contacts that tells us either the protein is folded or it's unfolded, and we can then calculate the relative free energies of those states, those different states. Or if we're looking at a phase transition, what we can use is something like the lattice vectors or the bond order parameters. And again, these reaction coordinates are telling us whether the system is ordered or whether it is disordered, because we know as we go from the solids to the liquid, we lose symmetry or order in these structures, and thus we can tell whether the system is ordered or disordered using these sorts of reaction coordinates. And the business of finding these reaction coordinates is arguably the most difficult thing about all of these methods. And that's where you really need your chemical or physical intuition. So you need to know something about the problem that you're looking at, and you need to basically know what it is you want to find out. Which sounds like a bad thing, but probably isn't, because if you don't know what you're looking for, then it's questionable whether you're going to extract anything out that is meaningful. So let's look at that a different way. So here is a video by someone you probably recognize. And this is showing us the problem that we encounter when we use just unbiased MD. This is this biased sampling problem that, because we have this high barrier here along our collective variable, the system, the little circle there, is not able to cross that on the short time scale that we have in an MD simulation. And thus we're trapped in this basin. And so when we calculate the histogram, we get a probability distribution that is not close to the real distribution. So it's not the correct free energy that we extract from that simulation, because we've not sampled all of CV space and all of phase space. So this is where what Giovanni was talking about last week with these bias potentials. So the idea is that we add some bias potential that acts on our collective variable to improve sampling. And very early on, it was suggested that the best bias potential that you could use was the free energy. So if you knew the free energy as a function of your CV, you could use that as a bias potential or some function of that, and then you would have completely flat sampling, and the thing would go back and forth, no problem, like this. Okay, so there we go. The timescale problem completely solved. All you need to do is use the free energy as a bias potential. Done. No problem. Except there's one major problem, which is that you don't know the free energy in general. So you can't use the negative of the free energy as a bias potential, because this is something that you don't. So the idea of metadynamics was that this was a bias potential that, in the limit of enough sampling, would converge to minus the free energy and that perfect bias. So that's where this idea came from. Okay, so what we're going to do is we're going to build an approximation of the free energy, and then we're going to use that to bias our sampling. And that's the way that metadynamics works. Okay, and then we can get out these free energies, and we can start to make these nice pictures to put in papers and to be able to say something about the behavior of these physical systems. Great. So why do we do this metadynamics? What's it for? Well, it creates beautiful images for the nature papers, particularly if you do it in 2 dimensions. You can make really nice pictures that look like things in the real world. So here, for example, you've got a free energy surface that looks like this IKEA table that is there. Here, someone is trying to phone home and send you a message. The free energy surface looks a lot like ET. Here, if it's got a beak and it goes quack, it's a duck. It's this free energy looks like a duck. This free energy is Super Mario. So we can make these nice pictures that we can put into various papers. And these pictures will also fascinate everyone. Everyone loves a free energy surface, including this cat here, which I don't know whose cat that is. So you can also make nice visualizations of how metadynamics works. So there's a small cottage industry visualizations for how metadynamics works. So Zheng et al. Use a cloud to explain how metadynamics works. Bernd Enzing uses this beautiful movie of a little man in a boat to explain how metadynamics operates. And you can see it rains and the valleys fill up with water, and then he can go and flow into different parts of the energy landscape in his little boat and thus explore all of phase space. And then last but not least, our American colleague Jim Fempner uses this bird bath, which no one really understands. But that's what he tells us how metadynamics operates. So there we go. That's the theory explained. We can now go on and go do the exercise, I guess. You've seen all the pictures, you've seen these movies. Do we need to do anything else? I guess we probably do. So let's introduce some actual maths to make this quantitative. So what we've got in metadynamics is we've got this history bias potential that acts on selective degrees of freedom or collective variables. Okay, so these are the collective variables that we've introduced at the beginning of the talk. And the bias in metadynamics has this functional form shown at the bottom of this slide. So we have a sum over all previous times, and then inside that sum, we have the exponential, we have basically a series of Gaussians. And the center of these Gaussians are at the points in CV space that you visited in previous times. So the way that I like to think of metadynamics, and I like to explain it, which is different from all those other different ways, is that it's like when Hansel and Gretel went into the woods. So if you remember Hansel and Gretel, they go into the woods and try and remember where they've been. They leave a trail of breadcrumbs behind them. Metadynamics is the same idea, but instead of breadcrumbs, you drop repulsive Gaussians. Okay, so we have these Gaussians that are centered at points in the previous parts of phase space. And there are lots and lots and lots of reviews on metadynamics that explain this theory in a lot of detail, which you can read. It's a cottage industry. Everyone who works in the field at some stage, it seems, writes a review about metadynamics where they explain all the theory. So there are lots of different places that you can read about this theory in more detail. Let's carry on. So the idea is you're dropping these Gaussian potentials behind you, and these are basically filling, it is these Gaussians that are filling the underlying energy landscape and allowing you to cross the barriers into the different minima in that surface, okay? So initially they fill initially if your system starts in B, that's filled up with Gaussians. Then after a while, the system hops over into A, that fills up with Gaussians. And then you've got A and B both filled up with Gaussians, and then you hop over into C. And that's what all those movies were showing on the previous slide as well. Okay, so there's that equation, the central equation of metadynamics again, with this history dependent of bias potential. So this sum over, so the outer sum is over previous times, and then this inner sum, which I'm pointing out, which you can't see, so I don't know why I'm pointing at it. The inner sum is over your different collective variables, okay? Because you don't need to just use one collective variable, you can use 2 or 3. So the sum from I equals 1 to D in there is a sum over collective variables. So what parameters do we need to choose in order to use this? So the first one is that we need to choose our CVs and the appropriate collective variables to use for the particular problem. And this is the most difficult and also the most important choice that you make. So you need to pick a small number, and these need to describe, they need to distinguish between the various basins, and they also need to not have too many barriers in orthogonal degrees of freedom. Now, metadynamics is often more difficult to converge than the umbrella sampling techniques that you looked at last week with Giovanni. And you may say this is a bad thing if you're dishonest. If you're dishonest and you just want your results to converge, then yes, okay, the fact that this is more difficult to converge is a bad thing. However, in other ways, it's a good thing, because if metadynamics is not converging, what it's telling you is that your CVs are not up to the task. So metadynamics gives you a way of determining, by running a metadynamic simulation, you see whether you really have a good description of the system using this small number of CVs that you've set up. So that's your collective variable, that's your first parameter. Then your second parameter is a kind of energy rate. So that's the speed at which you're modifying this history-dependent bias potential. And there's two parameters that control that in the original implementation of metadynamics. The first of these is the height of the Gaussians, that's the W. And the second of these is the frequency with which you add Gaussians. And obviously what you want to do is you want to basically add your Gaussians and provide sufficient time for the system to relax and accommodate itself. You don't want to just be piling Gaussians on top of each other. And then the last parameter that you've got to control is the width of your Gaussian, and there may be more than one of these widths. So the width of your Gaussian, the bandwidth of the Gaussian, basically the shape of the kernel that you're adding at each time. And we're going to talk about how to set those parameters in a minute. So, the advantages of metadynamics are that you do get the enhanced sampling along the CVs, you get the reconstruction of the free energy surface, and you don't need any a priori knowledge of the energy landscape, none at all. But what we're talking about here is the original implementation of metadynamics by Lau and Parinello in, I think, 2002, if I remember correctly. And there are disadvantages to that particular method. Firstly, the method, it can be difficult to converge and you can get overfilling. And a method that still is not really solved, and to a certain extent we don't actually want it to be solved, is that the choice of CVs is far from trivial. But for all of these methods, the choice of CV is not trivial. That's where the physics is. That's why you have to do a physics or a chemistry degree or a biology degree before you start doing research, because you've got to know something in order to find out something new. So to sort of resolve this problem of overfilling, there is, in 2008, a sort of new version of metadynamics came up, which is this well-tempered metadynamics, which you may have heard of. And basically the difference between well-tempered metadynamics and untempered metadynamics, let's call it the original implementation, is that the heights of the hills in well-tempered metadynamics decrease as a function of time. So you're kind of lowering that rate at which the hills, at which the bias is modified as the simulation progresses. And this has a number of consequences. So the first consequence, the final bias does not converge to the negative of the free energy anymore. It converges to a simple function of the parameters and minus the free energy. That's shown on that slide, the equation for V of S. And this may sound like a disadvantage. It isn't. What's really advantageous with this method is that this new parameter that we introduced, this delta t, it can be used to tune the extent to which our method now explores the CV space. So if you set this delta t to be small, then the system will still not cross really high barriers along your energy landscape, which is something you may want to happen. Because, for instance, if you're looking at a conformational rearrangement in some system, you probably don't want all those bonds to break, which would be some higher barrier to that process. So this is the method that most people using metadynamics now employ. They use the well-tempered variant and not the original variant. And the paper on this one, I think it's very easy to follow. It's a nice paper and you can reproduce all the derivations within that quite easily. And this is a useful exercise. So get yourself a copy of that paper, the PRL from 2008 by Barducci, Busi and Parinello, and see if you can have trying to reproduce the derivations in that paper. because it's not too difficult and it's nice and easy to follow. Okay, so if we're doing well-tempered metadynamics, what's happened to our parameters that we have to set? Are they any different from what we had before? Well, we now have, instead of setting the Gaussian height, we set an initial Gaussian height. So that's the first height of the hills, because remember, the hills are going to decrease the height as the simulation progresses. And basically, whenever I run a well-tempered metadynamic simulation, I set that initial Gaussian height equal to half KT. And that works fine. So just set it to half KT. And then you have this delta T parameter to set, which is how fast the amount of bias added decreases to 0. So to help you think about this, T plus delta T is, delta T is in units of temperature, and T plus delta T is the temperature that the CV is exploring phase space at. So we can think of when we're doing this well-tempered metadynamics, is we're doing dynamics along the CV at a higher temperature than we're doing the dynamics amongst all the other bits and pieces that is moving around. And the temperature that the CV is exploring at is T plus delta T. So you don't want that to be too high, because then you're crossing barriers that aren't going to be crossed at T plus delta T. So what people normally do is set that the parameter that you set for this, which is a bias factor, which is T plus delta T all over T, to around between 5 and 10. So your CV is exploring phase space at a temperature that is 10 times higher than the temperature of the system, or 5 times higher than the temperature of the actual system. And then you're crossing barriers that might be relevant, but you're not crossing barriers that are ludicrously high with this bias. Okay. So that's 2 of the parameters we've decided on. So the initial height we can just set to half KT. The bias factor we can set to between 5 and 10. So the only other parameters we need to choose are the sigma parameters, which are the widths. And the idea there, the way that we set these in general, is that you want to set these so that they're comparable to the widths of the features in the free energy landscape. So what you do is you run an unbiased simulation, you look at how much the system is fluctuating when it's unbiased, and you set the Gaussian width equal to the size of that fluctuation, so the size of the feature in the energy landscape. So based on what you're seeing in that simulation there, you would take all that data, calculate the variance from that data, square root it. That gives you the standard deviation of that band of data, and then you maybe use that as the collective, as the value of sigma. Okay, so that's relatively straightforward. Okay, and you try and do it in ideally the narrowest feature in the free energy surface, but it doesn't matter too much. If you set them a bit wide, it's not ideal. It's better to set them narrower than wider. And even here, there is the option, which not many people use, to adaptively change the shape of the Gaussians on the fly. So you can set them either in one unit and use the instantaneous variations to determine the size, the widths of the Gaussians, or you can basically set the width of the Gaussian in nanometers, and then go back through the Jacobians and work out basically what that corresponds to in the units of your collective variable. These are things you might want to explore. Adaptive hills, you can look at that and how that's done within PLUMED if you want. Okay. So we've already talked about the bias factor. Here I'm just showing you what I talked about in words on that previous slide. So basically your bias factor, it controls how much of phase space you're going to explore. So in panel A, you've got a small bias factor. In panel B, the bias factor is bigger. And in panel C, the bias factor is even bigger. And you can see you get out the same free energy from all these different simulations in the regions where you can actually calculate the free energy. But you can see that the exploration is different. So you can see that as you increase that bias factor, you're getting more exploration of that free energy landscape. But as I said when I talked about this the first time, usually a value for between 5 and 10 will do the job for most biological applications. Okay, so as I said, the most difficult choice is always the CVs. And your CVs, you want them to be able to discriminate between the relevant metastable states, which is should be the easiest thing to work out, because you should know in advance of running the simulation. You should have some vague idea of what the metastable states for your system look like. Otherwise, your sort of research question is ill-posed. You're not going to find out anything if you're just running simulations and hoping for the best. So you should have some idea of what the different metastable states are, and then you should be able to think of a variable that discriminates between those. The second of those points, including all the slow modes, that's more difficult because you don't necessarily know what's slowing the transitions between those different metastable states. So you don't know the pathways of that take you between those states. But as I said, compare umbrella sampling, where you can, for umbrella sampling, you still need the first one of those things. But you may find that you get a converged result and you get relatively small error bars, especially if you don't do the replica exchange tricks. But you're getting a result that's not actually real because you haven't included the slow modes of the process. Metadynamics, by contrast, if you've not set it up properly and if your CV doesn't include a slow mode, it will probably do something weird and it will look like, now this isn't working very well. So it at least gives you some clue as to whether your coarse-grained description is valid or not. And then the last one of these things that you need is a small number of CVs. We really can't do metadynamics with loads and loads of CVs, because it becomes very, very inefficient very quickly. So, as I said, if you've got a well-formed research question that you're trying to answer, you should be able to think of an initial guess for the CVs. If you're not able to do that, then you need to go back and rethink your research question. Now, having said that, there are ways that you can think of to design smarter CVs. So there's lots of people now looking at these questions with looking at trying to devise CVs using machine learning, and you'll find lots and lots of papers out in the literature with people using machine learning and various different flavors of this to design smart CVs. This is good, and it's a noble effort. Having done some of this myself, I think it does have value, but you still need those collective variables to discriminate between your metastable states, because you still need to have some research question that you're answering. The great thing about machine learning, the disadvantage of machine learning is you go off, you run your machine learning calculation, and your machine understands what's going on, but you don't. The aim really is for us to understand the results that we're getting, because we're not able to write a paper if we don't understand our own results. So you need to think, this is never going to go away. You still need to think of CVs that distinguish between the metastable states. You need to think about what those metastable states are for your system. So that, again, the machine learning is building to the automatic protocols. There are efforts to improve metadynamics to deal with larger numbers of CVs. And then a trick that's very popular is coupling metadynamics with methods like replica exchange. So you do parallel tempering and you've got metadynamics running at the same time. And the idea is you get quick convergence on the CVs that you're interested in from those simulations because you've got a bias potential driving the dynamics. But if you've got barriers in the transverse degrees of freedom, the parallel tempering is helping the system to cross those and explore more of phase space. But those multiple replica things, Giovanni will talk more about the theory of that next week. But thinking about metadynamics, what we need with all of these, and where this is where you need to go away and think about your own problems, is you need to know what the relevant metastable states are, and then once you've got those relevant metastable states, you can extract. You can work out what appropriate CVs are, because those CVs are going to give you your insight into the physical problem. And I think we've also talked about how sometimes the CV is actually the result of the paper. Working out what the right CV to use is giving you insight into those mechanisms as well when you're doing these metadynamics simulations. Okay. So we've talked about how in metadynamics, you have at convergence, the free energy as a function of the that you biased. But the nice thing is you can calculate from your metadynamics simulation the free energy as a function of any other state that you're interested in. So maybe there's some other metastable state that you might think was important. You didn't think that there was such a big barrier that you needed to bias in order to get crossings, but you want that information about the relative free energy of that state. Well, what you can do there is you can reweight and you can extract that free energy. Okay? Now, this is tricky with metadynamics and more difficult than you've seen in previous week where you had umbrella sampling. So the trickiness comes from the fact that the metadynamics bias, unlike the biases that you've seen last week and when we were doing the errors exercise, is time dependent. And as a consequence of that time dependence, lots of different people have come up with different strategies for dealing with that time dependence. So the sort of first of these was Max, and that appeared in that paper number 1. Then Giovanni came up with a method as well, which is the metadynamics with adaptive Gaussians. That method 2, you've seen before, because it's what we used in week 2. So this idea of just using the bias that we got at the end of the simulation, forgetting about the fact that the bias is time dependent and just using that as a static bias to weight our whole trajectory. So that's method 2. And that's fine in most cases and is cheaper than Max's method. The Tilroy method, which we mentioned at the beginning, what that does is basically it allows you, it accounts for that time dependence a bit better and maybe allows you to use the statistics that you've collected from the simulation in a more of the statistics. But essentially, it's the same idea. You just have, you're dealing with that time dependence in a better way. And then, last year, Ghiberti, Cheng, Cheriotti, and I, we came up with another method, which is based on the same idea of trying to basically use all the statistics from the trajectory a little bit within these sort of reweighting methods. But for most purposes, just assuming that the bias, using the final bias and assuming that it's time independent works fine in a lot of cases. And it's just a question of running the simulation for longer. Methods 3 and 4 might allow you to get out a more converged free energy surface from less simulation. But if you've got lots of computer time, why not just run to as long as you can and use that final bias method. Okay, so that's kind of the theory that Max wanted you to see before you dived into the exercise. I know you don't want me to talk through all the sections of the exercise, but what I think I'm just going to do is I'm just going to tell you quickly what each section is about and relate it to what I've said in this talk, just so that you can see like in 5-10 minutes, and then I'll let you go. Before I do that, does anyone have any questions about any of that theory before we just talk through the exercise? I'll take that silence as a no, that I was extremely clear. Excellent. So let's share. Oh, there we are. Share the screen. Okay. So you should now be able to see this, the website. We're going to do the metadynamics exercise 21.4 here. So let's go look at that. So we've got an overview of the theory, which I've explained, and references to all of these many reviews on metadynamics that you can look at. There are details about how to set up the software, but it's the same as you did last week for the Grovax. And then within all of this, you're going to be looking at alanine dipeptide. Okay, so alanine dipeptide, we looked at last week. It's our test case molecule. So you're going, because we know everything about alanine dipeptide, so it's a nice one because you can use it to understand a lot about the method. Okay, so there's alanine dipeptide, and it's the two torsional angles, yada, yada, yada. So first exercise is just running some MD to see that you have that timescale problem, to see that if you run this simulations of alanine dipeptide that is short, it doesn't cross those barriers. And that's what you'll see in that exercise. Exercise 2 gets you to run a metadynamics simulation. So it gives, you have the input for metadynamics, and then it's going to show you how you can do some hills, and you can extract out the free energy surface from the bias potential in the metadynamics simulation. And then it gives you a little exercise to do to look at how the free energy is converging. So the estimate of the free energy that you get is converging. So it gives you a little exercise there to look at. Then exercise 3 starts talking about how to reweight the metadynamic simulation. Now, you've done this sort of thing before. We're using exactly the same method here for reweighting as we used in the last exercise of 21.2. So the way that we reweighted that free energy surface for the Leonard-Jones, we're now going to use that to reweight the free energy, to get out the free energy surface by reweighting from our metadynamics simulation. Okay, and then it's all feeling, maybe you're all getting deja vu, but the next thing you're going to do is we're going to talk about the error bars, because the error bars are important, because we want our results to be reproducible. We're generating random numbers, so we need there to be error bars in these estimates. So exercise 4 talks about estimating the errors using block analysis. And again, this is exactly the same as the methods that you were using in Masterclass 21.2, okay? There's a script that Max has written for you to use, but the method underpinning it is the method that I showed you in exercise 21.2. And I think it's also the method that Giovanni was talking about last week in the context of umbrella sampling, because we're just assuming that the bias is static. Okay, so then we start getting a bit creative. So you basically got the idea of metadynamics from those first 4 exercises. So exercise 1 is showing you that there really is a timescale problem for this system. Exercise 2 is showing you how to do a metadynamics calculation to resolve that. Exercise 3 is showing you how to extract the free energy by reweighting. Exercise 4 is showing you how to do the block analysis and get the error bars. because we've talked about how important error bars are at length. Exercise 5, we start letting you be a little bit creative. So what we're encouraging you to do here, or what Max is encouraging you to do, is to basically try and run metadynamics on this alanine dipeptide, which we know everything about, with different CVs. So there's various different CVs that you can try and use to do this, to look at this alanine dipeptide system. And some of these CVs we know are truly terrible at driving the transition between the two states. And your job here is to try and investigate which CVs are terrible and which CVs are good, okay? And to help you with that, all you have to do is run the calculation. So you decide which of these CVs you're going to use, or if you're feeling super creative, you come up with some other CV yourself. And then what a result, post the free energy surface that you tried to extract on Slack, and talk about like whether you think the result that you got is good, or whether you think that the result you got is crap. And hopefully, and if you try this for different CVs, what you'll hopefully see is that what happens when you use a good CV and what happens when you use a bad CV. So this gives you a chance to experiment. And if you're using the Slack to comment on things, you're doing things in parallel. So you could even collaborate together, and you could say, for example, Oscar is going to do the dihedral, and Karen is going to do the radius of gyration, for instance. And then you can both post those results, and then on Slack you can talk about which one is good, which one is bad. Yeah. So that's kind of fun. So you can mess around and experiment with this method on this testbed system of alanine dipeptide. And then the last exercise that we've got here is a real meaty example. So we've got this quite complicated looking protein that undergoes this transition from an alpha helix to a beta sheet. So you're going to look at this all in implicit solvent. And it's up to you to try to work out what the appropriate CVs are, to work out how to run the simulation, and to try and extract that free energy surface with suitable error bars to post on Slack. And the important thing to bear in mind is that although this is not using like a full expensive simulation in explicit solvent or anything like that, but it is going to take a few hours to run that calculation. So if you want to get some results and have some insight on exercise 6 before Max does the wrap up in a week's time, you really need to be starting this by Friday at the latest, so that you've got some time to experiment and actually run your simulations. You're not going to be able to get any result for exercise 6 if you're starting this exercise at 10 o'clock next Monday morning and trying to get it done before the masterclass. Okay, so that's what I wanted to say. Max will be available all week. It's just today that he couldn't make it for the tutorial. And again, sorry about that. But he will be available on the Slack. So if you've got questions, please do get in touch. Please do try the exercises, post your results on Slack. We're curious to see what you do and what you try. It is an opportunity for you to experiment and explore this method. Because it's not that complicated. The theory of it is not that complicated. But what's difficult is the application and the various different CVs that you can use. But because you have this system that you can look at in all sorts of different ways, if you explore, the more you explore that alanine dipeptide system, the more insight you'll get into what it looks like when these calculations go wrong, and then when you go to do your really more complicated and more interesting simulations, you will get that insight. Okay. Great. Does anyone have any questions before we call it a day there? Or any comments? Nope. Okay then, well, if no one has any comments or questions, I think we can stop there then. Have a lovely week, and I'll probably see you again in a month or so when I'm doing dimensionality reduction. And I won't be pretending to be Max. I will be me. Okay?
Okay. Thank
Great.
you.
No problem.
you.
Thank you.
Thank you.
Bye-bye.